I mean, William could have introduced you better, Jack, but please, everyone, welcome Jack. Just speak next time.
Yeah, sure. Yeah, so I'm just going to briefly talk about my PhD work today. I'm working under Ian Watson in James Watt School of Engineering, trying to use machine learning to find ways to make biorefineries better. I like to use the tagline bigger, better, more, but it just makes me sound stupid. So I'll start by just saying like what biorefinery is. It's very similar to a petrochemical refinery, but the big difference is instead of using fossil fuels, you're using biomass. The biomass feedstock can be something that you grow, whether it's agricultural or terrestrial, whether it's terrestrial or like marine based, it's just something you grow. And it can also come from waste sources as well. The types of products also can be energy based, but there's a better, more valuable market looking at pharmaceuticals, cosmetics, and even like in foods. Although it's similar in sort of concept to a petrochemical refinery, it's a lot more expensive because it's not well established and developed industry. The motivation behind doing it is moving away from fossil fuels, reducing carbon emissions, and also shifting away from this linear consumption and production path, rather than making a product, using a product, and getting rid of it. And if you incorporate biorefineries into this concept of bio-circular economy, you will grow something or get a waste stream, turn it into something else, and use it, and then it feeds back into that waste. You've got this circular bio-econ going. So the types of processes you get in biorefineries, they can be thermochemical, physical, chemical, and biological. The desirable biorefinery has all of those going on all at the same time. It's a bit small down here, but it's the idea is you've got this dynamic, flexible, and complex process system with lots of processes all going on at the same time, all feeding into each other, recycling energy, recycling byproduct with lots of different feedstocks. This is why modeling would be very useful for this. Because this, as you can see, is a very dynamic and complex system that would be very susceptible to perturbations. Sorry about that. So pyrolysis is one of the processes that I'm looking at. Pyrolysis is where you take the biomass feedstock and you put it into a high temperature, low oxygen environment to break down the long carbon chains found in the feedstock into more useful chemical building blocks, which you can then use to make these added value products. The main products that come from the pyrolysis, it's split up into its solid, liquid, and gas components, and it's just called bio-oil, biogas, biochar. The properties of the gas, oil, and char is entirely dependent on the process parameters, whether it's the temperature, the heating rate, how long it's in there for, and also the feedstock characteristics. With a wide variety of possible feedstocks, and also process conditions, you can get a wide variety of properties on the oil, the gas, and the char. Sometimes you want to have a bigger, obviously, bigger yield of stuff like oil. In those cases, you have higher temperature and longer residency times, shorter residency times. But if you've got char and gas that you're wanting to promote, you might want to look at having a higher oxygen content in the feedstock as well as having short residency times and low temperatures. The modeling can be done using CFD kinetic balances and equations. But what tends to happen is you either put yourself in a very niche situation where it's very hard to apply it elsewhere and it's very computationally demanding, or you create a model that's too general that you can't apply it to a real world situation. So what I did was I started by looking at using machine learning. This is where machine learning comes in, obviously. I started using a random forest model. I'm going to briefly go through it very quickly because I'm sure that most people know how that works. But you've got a decision tree here, which will create a decision path based on some input parameters, and it'll follow the path all the way down to the bottom where it'll produce an output. That's one tree in the forest. You've got many, so you take an average of that result, and that's your output of the forest. The input parameters in this will be like these sort of characteristics and the process parameters. I'm also going to touch on it really briefly as well. That's very similar to random forests, except they differ in how that they're trained. These trees are all constructed at the same time using a bagging technique with different groups of data for constructing the trees all at the same time. But gradient boosting is a boosting technique, but it builds the trees sequentially and builds on weaknesses from the previous trees. And then again, very similarly, takes an average of all the trees in the forest for its output. So I started by constructing a database based on what was available in the literature for pyrolysis. I ended up constructing two very similar but slightly different databases. One that's much larger with many data points, but it's not as descriptive, so it doesn't have as many inputs describing the process conditions, but it has more data points in terms of the number of experiments that it's describing. And I have a reduced one, which has less data points, but more descriptors in terms of the conditions. The initial model wasn't great. Well, models, they weren't great. I was assessing them using the coefficient of determination, R squared, and this other accuracy metric, which I don't use anymore. But it's a measure of how far your prediction is away from the actual result. You want to get as close to 1 as possible. These aren't good scores for charcoal gas or oil. The models was very a simplistic approach when I first started doing it. But what I found in the literature was the lower end of stuff that was reported was about 0.7, and I'm nowhere near that for any of them. What I did find though, and something that's good with random forests, and a reason that was recommended to start with them, was they're not as black box as some of the other machine learning algorithms out there, and you can get some inference from models. And I found that the sort of importance they were putting on the parameters was somewhat encapsulating what was going on in the pyrolysis process. For biochar, gas, and oil, temperature is right there at the top, which is very important. And then for oil, you've got oxygen content as well, which would promote the creation of the other two. So rather than oil, and you've also got reaction time up there as well. So what I decided to do was, because the models weren't too good, was take a two-pronged approach. Look at introducing hyperparameter tuning into the models and an alternate algorithm. This was where gradient boosting comes in as another ensemble modeling algorithm. So very similar to random forest, but supposedly a bit more better when you tune. And then I also decided to revisit the data and clean it, go through every different source. Because the database was constructed from what I found in the literature, it did include other databases that other people had constructed, and I went into their databases, went to their sources, and then compared them to see how I could improve it, just to see if it was accurate, mainly. I found that, yeah, that was the case. There was something the basis that you use to describe the feedstock characteristic changed from source to source, and some people didn't update their databases for that. So I did that, and as a way of improving the data set. I also noticed that a lot of the data sets that were being used to train these models, they weren't as broad as incorporating as many different feedstock types as possible. A lot of them focused on like woody and straw biomass, lignocellulose and stuff. So in addition to cleaning this expanded and reduced data sets, I created a third one, which focused solely on microalgae feedstocks. As a way of, if I restrict, if it's not as broad, is it going to create a better model? With the hyperparameter tuning, I looked at using initially a random search and then a grid search, where the random search looks lots of different hyperparameters in a random fashion, and the grid search take the best performing parameters from that and then go through every different combination of all those, which is quite intensive. This did result in some model improvements with the random forests, as the ones on the left here. They're getting closer to that 0.7 of what you can see in the literature. In particular, when you go to the models on the left, you can see the random forest gradient boosting using just the microalgae stuff. That's when it gets a lot better as well. However, this is when I started looking at overfitting, and all the models at the moment are overfitting. The training scores for the coefficient of termination are much higher than the testing ones. It's a bit confusing because that actually metrics still in there. But if you look at here, if you get to the accuracy ones, you can quite clearly see that there is a big discrepancy between them. So just like before, I decided that it's not quite working, something's not quite right. So again, I decided to look at the algorithm. I decided to look at neural networks. This is the most prolific form of pyrolysis modeling that I found in the literature. It was everywhere. It seems to be what everyone was using. The only reason I didn't start with it was because I was told it's quite, it takes a while to get used to, and you should be able to do what you need to do with random forest. But I didn't. And then I decided to revisit the data as well. So I decided to review it and then enhance it through data imputation. Until now, when there was a blank in my data sets, I'd delete the entire row, which meant you'd lose a data point. And this was quite a lot because the the data came from lots of different sources. And there would be discrepancies in the experiments from source to source. So there's lots of data points that I was missing out. I decided to go use I decided to use 3 different data imputation techniques, 2 of which themselves are based on machine learning. I described it as sort of Ouroboros nature, that you're using machine learning to make machine learning models. It just seems a bit wrong, but I found examples of people doing it, so it gave me a bit of confidence. And then I used the inbuilt iterative computer package as well, which follows a more statistical base. In the imputation methods, you basically make an estimate based on all the other data that's available, and then you'll move on to the next missing point. And you do that until you fill all the blanks in the data, and then you'll run through it again until you meet a break condition or there's been adequate amounts of loops and you converge on a data point. I also decided to expand the collection of databases. I found another additional quite large data set on Kaggle, which I decided to use and not necessarily feed into the data sets that I had, but have it as a separate one just to check that my data set was working, or it was an issue with me. Wasn't. So I ended up exploring 15 different configurations of the neural networks. The neural networks themselves are obviously they're made up of lots of layers with nodes in them. connected by different functions. And then they're optimized in their training process using a certain choice of optimizer. That's sort of what made up the different configurations. Initially, I tried to narrow in on a choice of optimizer using a very shallow neural network. But that didn't help in any way. And it made me bang my head against the wall more when I kept on seeing stuff that says it's an art form, it's a trial and error. There's no actual strategy to doing it. So I created these 15 different configurations. And I also used 10 different databases. I'll go through them. So the first one's just the microalgae one, and then there's the reduced one, and the remaining 8 are variations of the CAGO dataset and the expanded dataset, undergoing different imputation techniques. One of the imputation techniques, I kept in the sort of method of deletion where if you've got a blank, you remove the entire row. Yeah, so I did that. What becomes very apparent is that, again, overfitting is an issue. You've got the training data being much higher than the testing. In some of them, it's a lot worse than others, especially when you look at the configurations. But it's evident that it's happening in all of them. On the databases, this dip here is the CAGO datasets. So it shows that the database that I constructed is producing better quality models than the CAGO ones. These in particular are the imputation ones as well, with database 3 being when there's the rows are deleted. The kind of scores that are being seen in literature, it ranges from anything from about 0.7 up to like 0.97. So there's achieving very high, strong performing neural network models. So the main points is, yeah, all the models are displaying features that suggest overfitting. Some of the configurations that are there are performing a lot worse than the others, and the CAGO database was worse than mine for these models. So, like I said before, that there was this problem of overfitting, so I decided to introduce this layer to do with dropout, which is where the connections between the nodes in the training construction phase are severed randomly to a certain level, and then they're reconnected in the testing phase to prevent there being an over-reliance on a certain route, certain nodes in the model. I didn't use all the configurations from that I initially started with, just using the more stronger ones with a variation, using the more stronger ones with, depending on their sort of level of overfitting, and also having a combination of single output and multi-output models. Some of the models I had both bio-oil, biochar, and biogas yields all coming out, but on some of them I just had one of those as the output. Just as I dropped some of the configurations, I also dropped the full performing CAGO databases as well, just to see if that would help improve the model performance on average databases. Introducing dropout did lead to a reduction in overfitting. The change in R-squared between the training and testing data did decrease over all the models. In some cases, if we look for configuration 16, which is one that came about because I accidentally didn't change one of the optimizers, and I left it in because it became one of the more stronger models of the ones that I created. But in most of them, if not all of them, it led to a decrease in the difference between training and testing R-squared. But for some of the models, especially the weaker ones, it just completely broke it. Config 1, if you look, the numbers that are next to each data point are actually testing R² value, and introducing dropout resulted in it just going straight to 0.1 and just it's not working, making no sense. Yeah. So introducing dropout seemed good. The sort of development process for these neural networks in process has been getting better. The initial exploration wasn't so good. Then using sort of multiple configurations and databases, so a little bit of an improvement. And then if I dropped the poor ones in that, you can see that there is getting better. Introducing the dropout again reduced that overfitting issue. And the next step would be to introduce some kind of level of hyperparameter tuning. I use random and grid searches for the random forest and gradient boosting ensemble algorithms, but those are a lot easier to train, they're less intense than the neural networks. And if I was to use random and grid searches for the neural networks, it would be a very intense, computationally expensive process. There is alternatives out there, which would be better. I've had like Bayesian optimization recommended to me, as well as genetic and like evolutionary optimization techniques that you can use. But then there's also the option to explore automation of this whole process, including the hyperparameters where the layers, nodes, optimizers, all these things are treated as hyperparameters, and you can use certain toolboxes. This is something that I'm just starting to do now, and you can develop strong models that way. So this is where we go back to pyrolysis. We've had a bit of a dive into why my modeling's not going too great, or it's getting better. You can use machine learning to create the models and then find these optimal points if you're restricted in your process. This isn't something new, this isn't something that's original, other people have done it. And here is an example for a paper where when you've got the flexibility on the particle size and how long the feedstock is in the pyrolysis reactor for, you can find the optimal point for increasing the bio yield. There's also another example that looks at biochar yield and also the characteristics of this char, whether it's characteristics of the char as well, but it's not just looking at bio-oil and the residency time and particle size. The idea would be to create these models that are strong and then use it with an experimental rig in one of the labs for pyrolysis to not only validate the model, find optimal conditions for this rig, and then also assess the generality of the models, because the rig itself hasn't fed any data into it, and it's got slightly different setup to what's going to be available in the literature in the databases that I've constructed. However, that second article that I mentioned that looked at biochar, it had strong performing models, but when it came to actually applying it, this is why it's important to validate the models with the experimental rig. It was good at predicting the biochar yield, but when it came to the actual properties of biochar, there was quite a big discrepancy between them. Yeah, so I'm here right now. This is where I'm doing. I'm trying to create accurate machine learning models for process, and create a framework that works. From that, move out to indicate optimal process conditions for a rig of the process. Hopefully, then develop that into getting data from that process, turning that into creating models from that data, modeling a rig there, and maybe in the future implementing some edge AI with the modeling and the training and the optimizing all happening on site. hopefully that could then lead to demonstrating some like potential scalability, taking it from a lab scale to a large scale with the right amount of data, maybe introducing some more stacking, looking at front end stuff, maybe market forecasting or feedstock characterization. And then maybe this is more of a big leap, seeing if it's applicable to using other processes in the biorefinery. But that's me. That's the end.